Hi everyone, and welcome back to our third video in our first series of videos on Chapter 5.
Sorry, I can't search for videos on Apple Watch.
In this example, we're going to deal with a situation where we have varying density. Okay, the last example we looked at, the density was the same throughout the material. So if we look at this tank here, this isn't our problem. This is just something to keep in mind. If this is a fluid-filled tank, its load distribution is going to go as the height, right? The fluid on top is going to press on the stuff beneath, and that sort of thing. So there's going to be more of a load the farther down you go. All right, so that happens even at constant density. Now, in our problem, what we have is a cylinder that has a constant cross-section that we're going to call A. We have it aligned along the long axis, along the x-axis of our coordinate system. And it's fluid-filled, but the density is not constant, which means the centroid is not in the same place as the center of mass. We're given that the density at any particular location is this density at point 0 times this function, 1 plus x over L. So where x equals 0, all right, the density is just density 0. When x equals L, the density is 2 times the density at point 0. So graphically, that's how that looks. All right, so we're asked to find the magnitude and location of the equivalent load. Just intuitively, you know that it's got to be to the right of the middle because the density is increasing to the right. All right, so we'll just keep that in mind. All right, here's our cylinder redrawn side view, and the green area right there is a differential section of width dx. This is x going this way. That little differential section has a weight, a differential weight dw. What we need to do is integrate that differential weight over the length of the entire cylinder, and that'll give us the entire load. Right, so now we're dealing with a fluid here, and we're given density, not weight. So we have to remember that density is mass divided by volume. So our force function, right, because gravity is the only force operating, mg, and then m changes because the density changes. G doesn't change. So we can pull g out of the integral. So force is the constant g times the integral of dm along the length of that cylinder. All right, so now density is the change in mass over the change in volume, or rewriting that differential mass equals the density times the differential volume. Now we're looking for this, right? So we have this, right? We have a function for density. And we also know volume also, because this is a cylinder of constant area. So we know that dV is going to equal the area, because that's constant, dx times the differential distance. Okay. So let's put this together. dm, putting these parts together, rho is rho 0 1 plus x over L. Okay, this is rho. And then A dx, this is V. Now we're going to rewrite F. Remember, F was G times the integral of dm. Right, so this is G times the integral of all this stuff over here. Rho 0 times 1 plus x over L A dx. All right, so let's pull out some constants here. F equals G. Rho 0 is a constant. A is a constant. And L is a constant. Well, but L is part of G, so we can't pull that. I was getting ahead of myself here. Okay, can't pull that one out yet. 0L. And we're left with this 1 plus x over L dx. All right, integrate that, and I'm going to keep our constants outside there for a moment, and this is going to be L from the integration of just 1 plus L squared over 2L equals G rho 0A times L plus L over 2. So the force equals 3/2 G rho 0 A L. All right, so we found total load. Now, where is it? Where does this act? The density is not constant. If the density was constant, since it's a uniform cylinder, we would know it would act in the middle. So we go back to our expression of moment over force. Remember, that was the integral from 0 to L of x times G rho 0 A times 1 plus x over L dx. Okay, so this is the weight of each section. Weight of each section. And this is, the x is the moment arm. Alrighty, and we got to put that over the total force, which we just integrated and found over there. So, okay, let's do this. So that's G rho 0A integral of 0 to L of x plus x squared over L dx. Okay, multiplying through by that x over here and taking my constants out. And that goes over F, which we found appeared to be 3/2 G rho 0 AL. All right, so we can do some simplification. We have a G in the top and the bottom. We have a rho in the top and bottom and an A. So our constants completely went away in the top. And when we do the integration, we have x squared over 2 plus x cubed over 3L integrate that from, or the limits of that are 0 to L over 3/2 L. Just keep working through that, and you end up, well, let's do another step. You get 2/3 times L squared over 3 plus L squared over 2, L squared over 3 over L. And when you go through that and simplify, 5/9 L. Okay, so that's the location of where the thing is going to be, and that makes sense because 5/9 is a heck of a is more than center, and that's what we expected. It's more to the right of center. All right, so that's an example of how you can treat a problem where the material does not have constant density. All right, that's it for now. The next one is going to be dealing with multiple load conditions, and that'll be our last video in this series.